1 light year. It's the most used distance in astronomy, and it's almost always used as a number, a figure in a headline, a caption under a photograph. Almost nobody asks the obvious next question. What would it be like to actually cross one? Not to talk about it, to be inside the ship, to feel the acceleration, to watch the sky through the window, live in the silence and count the years. That question has real answers, not guesses, measured, tested answers, worked out from the ground across 4 centuries. Some of them are stranger than anything science fiction has put on screen. Tonight, we'll take that journey properly, step by step, and by the end you'll know precisely what 1 light year asks of a ship, a body, and a mind. Now get yourself comfortable, hit subscribe, we begin. Let's start with the measurement itself, because almost everyone pictures it wrong, and not by a little. 1 light year measures 5.88 trillion miles, 9.46 trillion kilometers. Numbers that size stop meaning anything the moment you hear them, so hold on to something smaller. Light moves through empty space at 186,282 miles per second, 299,792 kilometers per second. At that speed, a single flash of light would circle the Earth's equator 7.5 times before you finished a breath. Now let it keep going, not for 1 second, for a full year, 31.5 million seconds of that, with no pause, no slowing, no stopping to rest. The ground it covers in that year is 1 light year, and that speed is not a rough figure inherited from old textbooks. Scientists have measured it so precisely that in 1983, the meter itself was redefined in terms of it. The length of your own stride is now defined by how far light travels in a fraction of a second. Here's what most people misunderstand about that number. Light speed is not a technical ceiling waiting for a better engine, the way the sound barrier waited for a better wing. Light speed is the rate at which cause reaches effect, the speed at which the universe delivers news about itself. Think of dropping a stone into still water. The ripple carries the information that something happened. Nothing in the pond can learn about the stone before the ripple arrives. In our universe, that ripple is light, and nothing outruns it. Not a signal, not a spacecraft, not a consequence. Push harder against that limit, and the universe doesn't yield. It edits something else instead. Hold that thought. We will need it. Let's put 1 light year into units that belong to our own neighbourhood. Astronomers measure home distances in astronomical units. 1 astronomical unit being the gap between the Earth and the Sun, about 93 million miles, or 150 million kilometers. Sunlight crosses it in 8 minutes and 20 seconds. Every sunrise you have ever seen was already 8 minutes old. 1 light year equals 63,241 of those. So shrink the whole thing. Let the Earth-Sun distance become 1 inch, about 2.5 centimeters, roughly the length of your thumb from the knuckle. In that model, 1 light year becomes almost exactly 1 mile, 5,270 feet, 1.6 kilometers of hallway. Now walk it in inches. Neptune, the outermost planet, orbits at roughly 30 astronomical units, 30 inches, 2.5 feet from the Sun, knee height. Beyond it, the Kuiper belt spreads from about 30 to 50 astronomical units, a broad ring of frozen bodies holding Pluto, Eris, and Makemake. In our hallway, that entire belt fits between your knee and your waist. Past that, the scattered disk, sparse, tilted, thinly populated, reaching out to several hundred astronomical units, a few dozen feet of nearly nothing. And that is where our record ends. Voyager 1 crossed the heliopause on August 25, 2012, at 121.6 astronomical units from the Sun. The heliopause is the outer wall of the Sun's exhalation. Our star blows a constant wind of charged particles outward in every direction, and that wind inflates a vast bubble around us. The heliopause marks where the push finally fails, where solar wind loses to the thin gas drifting between the stars. Hold your hand in front of a hairdryer and slowly walk backward. Somewhere in that room, the pressure stops registering and you feel only still air. That is the boundary Voyager 1 crossed. Voyager 2 crossed a different part of the same wall on November 5, 2018, at roughly 119 astronomical units. And that produced something nobody had predicted. The two probes left in different directions, 6 years apart, at opposite ends of the Sun's activity cycle. Models expected the bubble to breathe, inflating when the Sun is violent, settling inward when it quiets. The two crossings should have been found in noticeably different places. Instead, they matched almost exactly. Scientists at the Johns Hopkins University Applied Physics Laboratory have argued the boundary must be sturdier than the models assumed, held firm by an unexpectedly strong magnetic field outside it. The disagreement has not been settled. In our mile-long hallway, both crossings sit about 10 feet from the Sun. Ceiling height, everything humanity has ever launched in the entire history of spaceflight occupies the first 10 feet of a mile, 0.2% of a single light year. Beyond that wall, the Oort cloud begins, a shell of frozen bodies wrapped around the entire solar system. Current estimates place its inner edge somewhere between 2,000 and 5,000 astronomical units out. In the hallway, you have finally moved past the room you were standing in, 167 feet to over 400. But here is the problem. No one has ever seen the Oort cloud. Not once. No telescope has imaged it. No probe has sampled it. The Dutch astronomer Jan Oort proposed it in 1950 by working backwards, the way you might infer a leaking pipe you cannot see from the stains spreading across a ceiling. Comets kept arriving from every direction on enormous orbits, still icy, still fresh, as though drawn from a reservoir that had never been touched by sunlight. Something out there had to be supplying them. The inference is strong. The measurements are not. Where the cloud ends divides the field. Some models close it near 50,000 astronomical units. Others push it to 100,000. A few extend it toward 200,000. In our hallway, that is a difference between 3/4 of a mile and a half, and more than 3 miles. The boundary of our own solar system, uncertain by a factor of 4. And the Sun's gravitational reach may extend further still. Estimates for the Sun's Hill sphere, the zone where our star's grip still beats the pull of the wider galaxy, range from about 1 light year to roughly 2. That boundary remains genuinely unsettled. Sit with the consequence for a moment. Cross 1 full light year, and you may still be inside the Sun's territory. So the journey we are describing does not deliver you anywhere. Crossing 1 light year means leaving our own outskirts, the frozen, unlit suburbs of our own address. And those suburbs are not still. Long-period comets fall inward from that region on orbits lasting 1 million years or more. One trip around. Our species, by current estimates, has existed for roughly 300,000 years. A single comet's orbit out there can run 3 times longer than anatomically modern humans have been alive. Now, place yourself out there. Imagine standing at that 1 light year mark, inside a ship, looking back the way you came. The Sun is still the brightest thing in your sky. It still outshines every star around you, but no matter how good your eyes are, it never resolves into a disk. It stays a spark, 63,000 times more distant than it appears from your window at home. No warmth reaches your face. Nothing casts a shadow. There is no light to read by. A spark you could lose with a blink, bright enough to find, far too faint to feel. Then you turn around and look forward. Proxima Centauri, the nearest known star to the Sun, sits 4.2465 light-years away. Its brighter companions, Alpha Centauri A and B, lie at about 4.34. Sirius, the brightest star in Earth's night sky, waits at 8.6. Vega, near 25. Run the arithmetic on your position. 1 light year covers just under a quarter of the distance to the nearest star, 23.5%. In the hallway model, Proxima Centauri stands 4.25 miles away, and you have walked 1. Everything paid, everything endured, and the nearest other star is still more than 3 light years further on, which raises the obvious question: is that gap crossable at all? Something already crosses it, constantly. In 2017, astronomers detected the first confirmed object from outside our solar system passing through it, 1I Oumuamua. In 2019 came the second, 2I Borisov, and on July 1st, 2025, the Atlas Survey Telescope in Chile picked up a faint moving point that turned out to be the third, 3I Atlas. Its path was unmistakably open, a trajectory the Sun could never have produced. 3. I Atlas carries a velocity of 58 kilometers per second relative to the Sun, about 36 miles per second, roughly 130,000 miles per hour, the fastest of the 3 visitors. Guess how long an object moving that quickly needs to cross 1 light year? Just over 5,100 years. Had it begun such a crossing when the first Sumerian scribes were pressing wedge marks into wet clay at Uruk, around 3200 BCE, the beginning of written history, it would be finishing about now, and that object is almost certainly older than everything around us. Its galactic trajectory and enormous excess speed point to the Milky Way's thick disk, a population of ancient stars, implying an age somewhere between 3 and 11 billion years. A team at Oxford has estimated roughly 7 billion years, at about 2/3 statistical confidence, which would make it older than the Sun, older than Earth drifting between the stars for billions of years before our solar system existed. The void gets crossed, routinely, just not by anything we built. Voyager 1 is now receding from the Sun at about 38,000 miles per hour, 61,000 kilometers per hour, fast enough to circle the Earth in roughly 36 minutes. The fastest departure humanity has ever managed. At that speed, 1 light year takes approximately 17,600 years. Set that against something real. 17,000 years ago, human beings were working by animal fat lamplight deep inside the caves at Lascaux, painting bulls and horses onto limestone walls. Had we launched Voyager 1 on the day those painters set down their brushes, it would be crossing the 1 light year mark right about now, and it would still be nowhere, still inside our own gravitational outskirts, still more than 3 light years short of the nearest star. That machine was never built for this. Nothing we have built was. So the honest question is not whether 1 light year is far. The question is what crossing it would actually demand of us, of a vehicle, of a body, of a mind, and of the physics that governs all three. And the entire answer hangs on one decision made before launch: how fast you choose to go. Because speed is the only variable that touches everything else. Choose slowly, and the journey outlives civilizations. Choose quickly, and the universe begins charging you in currencies you never agreed to, in energy, in matter, in the behavior of light itself, and in something far more disturbing than any of them. Nobody advertises the price of going fast. Let's look at what it actually costs. The fastest object human beings have ever made is about the size of a small car, wrapped in a shield of carbon foam, and it flies directly at the Sun. On December 24th, 2024, NASA's Parker Solar Probe passed 3.8 million miles above the solar surface, around 6.1 million kilometers, closer than anything we have ever sent to a star. And in that dive, it reached 430,000 miles per hour, 692,000 kilometers per hour. Break that down into something a body can feel. That's 119 miles, 192 kilometers, crossed every single second. NASA's own comparison for the flyby: fast enough to travel from Philadelphia to Washington, D.C. in 1 second. The team at Johns Hopkins put it another way: Washington to Tokyo in under a minute. Now, aim that speed at 1 light year. Guess how long it takes? Not decades, not centuries, roughly 1,560 years. Set that against real history. Launch in the year 466, while the last Western Roman emperors were still nominally on the throne, a decade before that empire ended, and you would be arriving right about now. Every language you have ever heard spoken would have formed, split, and drifted during the cruise. Every nation on the map would have been born mid-flight. And here's the part that quietly undermines the whole comparison. Parker doesn't hold that speed. The sun's gravity whips it up at closest approach, then hauls it straight back. That record velocity lasts hours, not centuries, and the probe isn't leaving anywhere. It's falling in circles. We have never built anything that could hold a speed like that. Let's be precise about what different speeds actually buy us across 1 light year, measured from Earth. At 10% of light speed, the crossing takes 10 years. At 20%, 5 years. At half the speed of light, 2 years. Push to 90%, and the gap closes to about 13 months. At 99% of light speed, just over 12 months. Look carefully at the top of that ladder, because something strange happens there. Climbing from 10% to 50% saves you 8 years. Climbing from 90% to 99%, a brutal, punishing increase, saves you roughly 1 month. The returns collapse exactly where the difficulty explodes. So why would anyone chase that final stretch for a month? The reason has nothing to do with distance, and everything to do with something the universe does to a clock. Hold on to that question. First, the engine has to exist. Nothing reaches these speeds instantly, and the reasons are both mechanical and biological. Acceleration is measured in g, 1g being the pull you feel from Earth's gravity, the weight of your own body in a chair. A high-performance car launching from a standstill presses you back at roughly 1g. Fighter pilots in pressure suits can tolerate 9g, but only in bursts measured in seconds, and even then vision fails as blood drains from the eyes. Sustain high acceleration, and the crew simply stops being conscious. The ship has its own limit too. Every gram of structure has to survive its own multiplied weight, indefinitely, which leaves one elegant answer. 1g, held steadily, for as long as the fuel lasts. The beauty of that number is what it hands you for free. A ship accelerating at 1g generates Earth-normal gravity throughout the cabin. No spinning ring, no rotating drum, no engineering at all. You would stand, walk and sleep exactly as you do at home, and the floor would be the wall the engine pushes against. At 1g, reaching 10% of light speed takes about 35 days. 5 weeks, 1 billing cycle. Reaching half the speed of light takes roughly 200 days, about the length of a school year. Reaching 90% takes close to 2 years of continuous, unbroken burn. 2 years of thrust is survivable. Humans have spent longer than that in orbit. The durations were never the problem. Here is where the story cracks open. To understand what these speeds truly cost, you have to stop thinking in litres of fuel and start thinking in mass itself. Every kilogram of matter contains a locked reservoir of energy, about 90 petajoules. That number is meaningless until you convert it. 90 petajoules equals roughly 21 megatons of explosive force, larger than the biggest nuclear device the United States ever detonated, somewhere near 1,400 Hiroshima-scale bombs. That's what 1 kilogram is, fully unlocked. 1 kilogram, a bag of sugar, a litre of water. The book on your shelf. Now the bill. To accelerate a single kilogram to 90% of light speed costs around 117 petajoules. More energy than that kilogram's entire mass contains. Translate it. Every power station on Earth running together generated about 31,800 terawatt-hours of electricity last year, according to the energy analysts at Ember. Feed all of it, every reactor, every dam, every turbine, every solar panel on the planet, into 1 kilogram, and you would need roughly 9 hours of the world's entire electricity supply. For 1 kilogram, a paperweight. Scale it to something that could actually carry people. Take a modest 1,000-ton vessel, lighter than a naval frigate, about 2.5 fully loaded jumbo jets. Accelerating that to 90% of light speed would consume something close to 1,000 years of all the electricity generated by human civilization. And then you have to stop. Deceleration is the forgotten invoice. A ship arriving at 90% of light speed doesn't arrive, it disintegrates. Slowing down costs the same colossal sum all over again, so the honest figure doubles. 2,000 years of planetary output for 1,000 tons, one way. Nobody plans a journey and forgets the brakes. But almost every discussion of interstellar travel does, and the arithmetic gets worse in a way Konstantin Tsiolkovsky worked out in 1903, before anyone had flown anything. His rocket equation captures a cruel loop. The fuel you carry has mass, so you must accelerate the fuel as well as the ship. Then you need extra fuel to accelerate that fuel, then more still. Picture crossing a desert on foot carrying your own water. Every extra bottle lets you walk further. But every bottle is weight you must also carry, so each one buys less than the last. Push it far enough and the load becomes absurd before the distance is covered. That's the shape of the interstellar fuel problem. Not a straight line. A curve that turns almost vertical. So what if we use the most energetic substance the universe permits? Antimatter. When matter and antimatter meet, they annihilate, converting almost their entire mass into energy. CERN describes the process as roughly 50 times more efficient than nuclear fusion. Nothing in known physics does better. This is the ceiling, not a stepping stone. Now, the reality check in CERN's own accounting. Their antimatter factory delivers around 400 million antiprotons per hour. Run the whole facility non-stop for a year, trap every single atom with no losses, and you would accumulate about 30 million antihydrogen atoms. Annihilate that entire year's harvest at once, and CERN estimates you would release a few thousandths of a joule, comparable to tapping a phone screen with a fingertip. Count every antiproton the factory delivers in a year, and the total comes to roughly 500 joules, enough to light a 100-watt bulb for 5 seconds. A starship needs tons. The gap between 5 seconds of light bulb and tons of fuel runs to more than a dozen orders of magnitude. Not a funding problem, not an engineering schedule. A gap that would swallow every accelerator humanity could conceivably build. And even if you had it, you couldn't keep it. Antihydrogen has to be suspended in magnetic fields, touching nothing, because contact with ordinary matter means instant annihilation. CERN currently reports storage times of up to about 100 hours, a little over 4 days. A voyage needs decades of perfect containment. We have 4 days. Let's look at what humanity has genuinely put on paper, because 3 serious attempts hit 3 completely different walls. Project Orion ran from 1958 to 1965 at General Atomics, built on an idea from the mathematician Stanislaw Ulam, and developed by Ted Taylor and the physicist Freeman Dyson. The method was almost violent in its simplicity. Eject nuclear bombs behind the ship and detonate them against a massive pusher plate mounted on enormous shock absorbers. Imagine standing on a shield while someone strikes it with a sledgehammer, over and over, the blows softened by giant springs into a steady shove, thousands of times. That was the engine. Dyson ran the trajectories for the largest versions and found something remarkable. 3 to 5% of light speed looked reachable, putting Alpha Centauri within about 44 years. Small test models flew on chemical explosives. The physics held. Then the 1963 Partial Test Ban Treaty prohibited nuclear detonations in the atmosphere and in space, and funding vanished entirely by 1965, after roughly $11 million across 7 years. Dyson later observed that this was the first time in modern history that a major branch of human technology had been shut down for political rather than technical reasons. Not physics, policy. Then came Project Daedalus, a study by the British Interplanetary Society from 1973 to 1978, led by Alan Bond and Tony Martin. Fusion propulsion, 2 stages, aimed at Barnard's star 5.9 light-years away, cruising at 12% of light speed, a 50-year mission. The launch mass came out at 54,000 tons, half the displacement of an aircraft carrier, assembled in Earth orbit. 50,000 tons of that was fuel, and roughly 30,000 tons of it had to be helium-3, which barely exists on Earth. The study's solution: mine it from the atmosphere of Jupiter using balloon-supported robotic factories over a 20-year operation before the ship could even depart. And Daedalus carried no brakes. It was a flyby, decades of preparation for a few hours of data as it tore past. The most recent attempt went the opposite direction, smaller instead of bigger. Breakthrough Starshot, announced in 2016 by Yuri Milner, alongside Stephen Hawking, with $100 million pledged. No fuel on board at all. Instead, gram-scale chips on sails a few meters across, pushed by a ground-based laser array approaching 100 gigawatts, up to 20% of light speed. Proxima Centauri within roughly 20 years of launch. By September 2025, Scientific American reported the program on indefinite hold. Public accounting suggested about $4.5 million actually spent, spread across roughly 30 contracts, against that $100 million promise. The project's leader, former NASA Ames director Pete Worden, described it as paused and being transitioned elsewhere. 3 attempts, killed by treaty, by Jupiter-scale logistics, and by money. Some proposals never got that far, because scientists are still arguing about whether they can work at all. The most elegant idea in the field belongs to Robert Bussard, published in 1960. Don't carry fuel, scoop it. Interstellar space holds thin hydrogen. Deploy an enormous magnetic funnel, gather that hydrogen as you fly, fuse it, and thrust with it. A ship that eats the road ahead of it. Robert Zubrin and Dana Andrews examined the scoop closely and found a devastating problem. Grabbing those ions and dragging them up to the ship's velocity produces drag, and in their analysis, the drag exceeded the thrust the engine could generate. The funnel breaks you harder than the engine pushes. Their work redirected the concept into a different use entirely. The magnetic sail, a scoop used deliberately as a brake. Defenders point out that the calculation depended on specific assumptions about exhaust velocity and available power, and doesn't automatically condemn every possible design. A 2022 reanalysis by Peter Schatzschneider and Albert Jackson revisited the scoop physics and found the practical requirements enormous. The drag side currently holds the stronger position. The argument itself has never fully closed. Then there's the idea that would bypass all of this: warp drive. Miguel Alcubierre showed in 1994 that general relativity permits a bubble of contracted and expanded space. But the solution demanded negative energy, exotic matter nobody has ever observed. Then more recently, Eric Lentz, along with work by Alexei Bobrik and Gianni Martira, proposed families of solutions claimed to need only positive energy. Ordinary stuff. That claim has not survived contact with its critics. Jarrett Santiago, Sebastian Schuster and Matt Visser argued in Physical Review D in 2022 that generic warp drives violate the null energy condition regardless, and subsequent analyses found energy condition violations inside the positive energy solutions themselves. Bobrik and Martyr have also noted a planar gap. No published warp solution can even change its own velocity. Fair reading of the evidence, the rebuttals currently have the better of it, and the exotic matter requirement has not gone away. So let's talk about what we could actually launch. The most credible plan on the table is the Interstellar Probe Study, led by Ralph McNutt at the Johns Hopkins Applied Physics Laboratory and funded by NASA. A launch window opening around 2036, a spacecraft of about 860 kilograms, a close gravity assist at Jupiter, and a resulting cruise roughly twice Voyager 1's speed. Design life, 50 years. Communications built to work from 1,000 astronomical units out. Real hardware, real engineering, no breakthroughs required. At that pace, around 7 astronomical units per year, 1 light year would take approximately 9,000 years. 9,000 years ago, on the Konya Plain in what is now Turkey, people were laying the first mud brick houses of Çatalhöyük, one of the earliest farming towns on Earth. Launch that probe then, and it would be finishing its first light year today, with everything since, agriculture, writing, empire, electricity, spaceflight, happening while it coasted. That's the best plan we have. So the engine remains unbuilt. Every honest path forward either violates a treaty, requires industrial infrastructure around Jupiter, needs a fuel we produce 5 seconds of light bulb from each year, or sits inside a dispute physicists have not settled. Grant it anyway. Suppose the engine exists, because the moment you actually move at these speeds, a second bill arrives. One no reactor, no laser array, no antimatter trap can pay. Something happens that has nothing to do with distance or fuel or structural strength. The universe begins editing time. The editing began in 1905 in a patent office in Bern, with a question so simple that almost nobody had thought to examine it. What does it actually mean for 2 things to happen at the same time? Isaac Newton had assumed the obvious answer. Time flows everywhere at one rate, the same for every object in the universe. One enormous town clock hanging over creation, and every person, planet and particle reading the same face. If 2 events happen together, they happen together for everyone, everywhere, forever. Albert Einstein published a paper that year with a dry title on the electrodynamics of moving bodies, and inside it he demonstrated that Newton's assumption is false, not approximately false, not false in some extreme corner of physics, structurally, fundamentally false. Einstein later explained it with an image anyone can hold in the popular book he wrote for general readers, published in German in 1916. Picture a long train running down a straight track at enormous speed. You stand on the embankment beside it. 2 bolts of lightning strike the track, one at the front of the train, one at the rear, and from where you stand, the light from both flashes reaches your eyes at exactly the same moment. You are precisely midway between them. Your conclusion is unavoidable and correct. The strikes were simultaneous. Now shift to the passenger sitting at the exact center of the moving train. While the light is in flight, she is moving. She is rushing toward the flash from the front and away from the flash from the rear. Light travels at one fixed speed for her, exactly as it does for you. That is the one thing the universe refuses to negotiate. So the front flash reaches her first. Her conclusion is also unavoidable, and also correct. The lightning struck the front of the train before it struck the back. 2 observers, 1 event pair, 2 irreconcilable answers about the order of events. And here's what makes it profound rather than merely puzzling. Neither of them is mistaken. No experiment can settle who is right, because the question has no absolute answer. Simultaneity is not a property of the universe. Simultaneity is a property of your motion. So the town clock picture has to go entirely. Replace it with this. Every object in the universe carries its own watch strapped to its own wrist, and the rate that watch ticks depends on how that object moves relative to you. Not the appearance of the rate. The rate. 2 watches, set side by side, and synchronized perfectly. Separate them, move one, bring them back, and they no longer agree. Not because one broke, because time is local and they took different paths through it. The conversion between any 2 of those watches has an exact value, worked out from the mathematics developed by the Dutch physicist Hendrik Lorentz, and it carries his name, the Lorentz factor. Think of it as an exchange rate between clocks, the way a currency rate converts between 2 denominations. Feed in a velocity, and it tells you precisely how much slower the moving clock runs. Now, this is exactly the point where a reasonable person becomes suspicious. It sounds like philosophy dressed up in mathematics. a thought experiment about trains proves nothing about the real world. So, let's look at what we have actually measured. 20,200 kilometers above your head, about 12,500 miles. A constellation of satellites is orbiting at roughly 14,000 kilometers per hour, close to 8,700 miles per hour. Each one carries atomic clocks, and the entire global positioning system works by comparing the timing of their signals. Those clocks do not keep Earth time. They can't. Their speed slows them, exactly as the Lorentz factor demands, by about 7 microseconds per day. But their altitude sits them in weaker gravity, which speeds them up by about 45 microseconds per day, a separate effect from general relativity, pulling in the opposite direction. The two do not cancel. The net result, every satellite clock runs about 38 microseconds per day, fast compared with a clock on the ground. 38 microseconds is 38 millionths of a second, far below anything a human nervous system could ever register. But the system measures distance by timing light, and light crosses about 11 kilometers, nearly 7 miles, in 38 microseconds. Leave it uncorrected, and your position drifts by roughly 10 kilometers a day, about 6 miles. A navigation fix would fall apart within minutes. The whole constellation would become useless inside a single day. So engineers build the correction in before launch. Each satellite clock is deliberately set to run slow on the ground, at a very slightly lower frequency, so that relativity will speed it up to the correct rate once it reaches orbit. The clock is made wrong on Earth in order to be right in space, and they tested it. In 1977, a satellite called NTS-2 carried the first cesium clock into orbit with the relativistic offset built as a switch. Engineers ran it for about 3 weeks with the correction turned off, watched it drift at precisely the predicted rate, and then switched it on. Every time your phone tells you where you are, it is quietly assuming Einstein was correct. Roughly 15 kilometers above the ground, about 9 miles up, higher than any airliner flies, cosmic rays from deep space slam into the upper atmosphere and shatter air molecules. Among the debris are particles called muons, heavier cousins of the electron, unstable and short-lived. A muon at rest survives, on average, 2.2 microseconds. Let's be precise here, because almost every popular account gets this wrong. That figure is the mean lifetime, not the half-life. The half-life is shorter still, around 1.5 microseconds. Mean lifetime means the average survival time, the point by which most of a population is already gone. In 2.2 microseconds, even travelling at the absolute cosmic speed limit, a muon covers only about 660 meters, 2,160 feet, 4/10 of a mile. They are born 9 miles up. They need to cross more than 20 times their own maximum reach. Run the Newtonian arithmetic and the answer is brutal. Something like 1 muon in 10 billion should ever reach the ground. They arrive constantly. Right now, as you sit there, muons are passing through your shoulders, your chest, the floor beneath you. Dozens every second through an area the size of your hand. David Frisch and James Smith measured the discrepancy carefully in 1963. They counted muons at the summit of Mount Washington in New Hampshire at about 1,910 meters, roughly 6,270 feet, recording around 565 decays per hour. Then they counted at sea level in Cambridge, Massachusetts, and found about 409 per hour. Without time dilation, the expected number at sea level was about 31. From their numbers, the muons' clocks were running slow by a factor of roughly 8.8. The particles were living almost 9 times longer than a stationary muon can, because from their own point of view, the trip barely took any time at all. In October 1971, the physicist Joseph Haffel and the astronomer Richard Keating did something almost absurdly direct. They bought seats on regularly scheduled commercial flights, loaded 4 cesium atomic clocks into the passenger cabin, and flew around the world, once eastward, once westward, while identical clocks stayed behind at the United States Naval Observatory in Washington. Their calculations predicted the flying clocks should lose about 40 nanoseconds going east and gain about 275 going west, because the eastward flight adds to Earth's rotation while the westward flight subtracts from it. The measured results: 59 nanoseconds lost eastward, 273 nanoseconds gained westward. A nanosecond is a billionth of a second. The time light needs to cross about 1 foot, 30 centimeters. 273 of them would not register in any human experience ever, but that was never the point. The point was that the clocks disagreed by exactly the amount predicted, in exactly the directions predicted, using hardware you could carry in a suitcase. Now let's put actual numbers on that conversion, because this is where the story turns. At 10% of light speed, the Lorentz factor sits at about 1.005, half of 1%. Effectively nothing. A crew would lose about a day and a half over a year. At half the speed of light, the factor rises to roughly 1.15. Noticeable, but manageable. At 90%, it reaches approximately 2.3. Time aboard now runs at less than half the rate it does at home. At 99%, the factor jumps to about 7.1, and at 99.9%, it climbs to roughly 22. Look at the shape of that. Flat, 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 then vertical. Earlier there was a question left hanging. Why would anyone endure the punishing cost of climbing from 90% to 99 when it only saves about a month of travel time? Here's the answer. It saves a month of Earth's time. It saves years of the crew's life. So take the crossing we have been building toward at 99% of light speed. Earth measures the trip at 1 year and about 4 days. 369 days of calendars turning, seasons passing, news arriving. Aboard the ship, the crew measures about 52 days, 7 weeks, 1 summer. Now hold both of those in your mind at once, because this is not an illusion or a measurement error or a trick of perspective. Both are literally true. The crew crosses 5.88 trillion miles, 9.46 trillion kilometers, a distance that light itself needs a full year to cover, and they personally live through less than 2 months while doing it. Imagine you are aboard. You would notice nothing strange. Your watch behaves normally. Your heartbeat feels normal. Coffee cools at the usual rate. 52 mornings pass. You sleep 52 times, and the interior of that ship is a perfectly ordinary place where nothing about time feels wrong at all. Then you look at the calendar Earth is keeping, and a year has gone. Extend it to a return trip, out 1 light year and back, and Earth records about 2 years and 1 week. Aboard, roughly 104 days pass. 3.5 months. Make it personal. You leave a 10-year-old child at home. You experience 1 season away. You come back and that child is 12, has changed schools, has grown 4 centimeters, and holds 2 years of memories you were not present for, and nothing anywhere can fix that. This is the part that unsettles people most once it lands. The gap is not a delay you catch up on, not a lag you correct once you're home and the clocks are side by side again. No mechanism exists, not in engineering, not in physics, that resynchronizes those 2 clocks. The time did not go missing, it was simply never lived. 2 rivers that separated in the mountains do not rejoin at the same height, and the view from the other direction is stranger still. Everyone at home spends those years writing to someone whose clock has slowed almost to stillness, sending news, decisions and questions to a version of a person who is still, from their own experience, only a few weeks into the journey. Now, a fair objection. All of this rests on theory, and theory can be wrong. Except this particular framework has been under continuous attack by people who would love to break it for more than a century. And it keeps holding at every energy scale we can reach. The cleanest demonstration came from CERN in 1977, when a team led by John Bailey injected muons into a storage ring 14 meters across, roughly 46 feet, at 99.94% of light speed. The Lorentz factor for that velocity is 29.33. A muon at rest lives about 2.2 microseconds. In the ring, those muons were measured living approximately 64.4 microseconds, stretched by a factor matching the prediction to within about 1 part in 1,000. And one detail in that result deserves attention. Circling that ring subjected the muons to centripetal accelerations on the order of 1 billion times Earth's gravity. being flung around a curve that violently changed the decay rate not at all. Time dilation tracked velocity, precisely as written, and ignored everything else. This is not an untested extrapolation dressed up as fact. This is applied, confirmed, daily use physics, running inside your navigation system, verified in the atmosphere above you, measured in laboratories, and built into the design of machines that would fail without it, which forces a set of consequences that mission planners have never had to confront, because no vehicle we've built has ever moved fast enough to make them real. A crew and their home planet would need separate calendars, separate legal timelines for contracts, ages, custody, inheritance, employment, criminal statutes, all of which assume a shared clock that no longer exists. Separate mission records with every log entry carrying 2 timestamps that cannot be reconciled into one. And planning itself would have to abandon the most instinctive word in human language. Now becomes a quantity with no universal value, not unknown, not merely delayed, but genuinely undefined between the ship and the people waiting for it. So the clock has been rewritten. The calendar has split, and none of that is visible from inside the ship. To see what these speeds actually do, the crew would have to look outward through the forward window, because at these velocities, the sky is no longer the sky. Step up to the forward window and look out at what these speeds have done to the universe. Films have trained all of us to expect one particular image, stars stretching into long white streaks that slide past the hull, the way headlights smear in a long exposure photograph. Every space film you have ever watched shows you a version of it. That image is wrong, not stylized, wrong. And here's what matters most about what you would actually see. None of it is speculation, not one detail. Everything ahead follows from optics we have measured for over a century, using the same equations that describe an ambulance siren passing you in the street. So let's look at what the window would really show. You already know the first piece of this because you have heard it with your own ears. An ambulance approaches and the siren sounds high. It passes, and the pitch drops, instantly, audibly. Nothing changed inside the siren. The sound waves ahead of the vehicle get crowded together as it chases them, arriving more often, sounding higher. Behind, they get stretched, arriving less often, sounding lower. Light does exactly the same thing. Move toward a source, and its waves crowd together. The light shifts toward the blue end of the spectrum. Move away, and they stretch. The light slides toward red. Astronomers call it Doppler shift, after the Austrian physicist Christian Doppler, and they use it every day to measure how galaxies move. But here's what most people misunderstand about it. Blue shift does not tint a star blue, the way a filter would. The entire spectrum slides sideways. Everything the star emits moves up together. Its infrared becomes visible. Its visible becomes ultraviolet. Its ultraviolet becomes X-rays. The whole ladder shifts by one amount, and your eyes only ever see the rungs that happen to land inside the narrow band they can detect, which means at high speed, you stop seeing the light a star sends. You start seeing light it sent from a completely different part of its spectrum. At 10% of light speed, the shift ahead comes to about 11%. Stars in front of you look faintly bluer, stars behind faintly redder, the sort of difference you would need instruments to confirm. Barely a change at all. At half the speed of light, the forward shift factor reaches about 1.73, and the sky begins to lie to you. Our own sun burns at roughly 5,770 Kelvin, that ordinary yellow-white you see at midday. Seen from a ship moving at half-light speed, a star exactly like the sun would read as though it burned at close to 10,000 Kelvin. Blue-white. It would look like Sirius or Vega, one of the hot, brilliant stars we pick out of the winter sky. And an orange-red dwarf burning at around 3,500 Kelvin would now look yellow, a sun-like star that isn't one. Every star ahead has been promoted. The entire forward sky has been reclassified into something no astronomer would recognize. At 90%, the factor climbs to about 4.4, and something stranger happens. That sun-like star now reads as though it burned at 25,000 Kelvin, the temperature of a massive blue giant, except most of what a star that hot emits sits in the ultraviolet, and your eyes cannot see ultraviolet at all. So the familiar stars don't just change colour, they drain away. Their visible light has been pushed straight past the top of your vision, and the sky ahead begins going dark in a way that has nothing to do with distance. But look at the same moment from the other direction, the light now entering your eye as ordinary green left its source at about 2,200 nanometers, deep in the near-infrared, a wavelength no unaided human has ever perceived. Objects that emit almost nothing in visible light, failed stars too cool to ignite, dust-wrapped protostars still forming, the cold dregs of the galaxy come climbing up into view. Sit with the consequence for a moment. The forward sky at 90% of light speed contains stars that no human being has ever seen. Not new stars. The same universe, unchanged, simply rendered in a band our eyes were never built to receive. A room you have stood in 1,000 times, lit for the first time by a different lamp. At 99%, the shift factor reaches roughly 14. What arrives at your eye as green light departed its star at about 7,000 nanometers, mid-infrared, the wavelength of ordinary warmth, the band a thermal camera works in. Everything a star emits in visible light is now far into the ultraviolet, well past anything the human retina can register. The sky is still there. Your eyes have simply been handed the wrong keys. Colour is only half of what the window shows. The other half is geometry, and it produces the strangest sight of all. Picture driving through steady vertical rain. Parked, the drops fall straight down onto your roof. Drive fast, and the same drops appear to slant toward you, striking the windscreen at an angle, not because the rain changed, but because you are moving into it. Light behaves the same way. Astronomers call it aberration, and they have measured it in starlight since the 1720s, caused by nothing more than Earth's motion around the Sun. At relativistic speed, the effect stops being subtle and becomes overwhelming. At half the speed of light, everything occupying the entire forward hemisphere of the sky, half of all creation, from dead ahead to straight out your side windows, compresses into a cone about 60 degrees across from the center. At 90%, that same half of the sky squeezes into a cone of roughly 26 degrees. Hold your fist at arm's length. That cone is about 2 fist widths wide. Half the universe, packed into it. And the region outside that cone goes almost completely black. Not because anything vanished. The light that used to arrive from your sides has been swept forward, redirected by your own motion, like standing in a downpour that suddenly blows entirely into your face. At 99%, the compression becomes extreme. Half the sky now falls inside a cone about 8 degrees from dead center, roughly the width of your thumb at arm's length. Run the geometry further, and you find that more than 93% of the entire celestial sphere has been crushed into a circle just 30 degrees from the direction of travel. Everything crowds toward one blazing point in front of the ship, and the compression concentrates the brightness with it. Forward intensity rises by something like 40,000 times at 99% of light speed. Whatever remains visible ahead is not merely gathered, it is ferocious. Behind you, the opposite. A sun-like star viewed astern would be redshifted so severely that it reads as a 400 Kelvin object, cooler than a domestic oven, radiating only in infrared. Invisible. The rear of the ship faces a darkness more complete than anything that exists in the real sky. One more thing fills that forward cone, and almost nobody thinks about it, because on Earth we cannot see it at all. The cosmic microwave background, the leftover heat of the Big Bang itself, released about 380,000 years after the universe began, now cooled to 2.725 Kelvin, roughly minus 455 degrees Fahrenheit, minus 270 Celsius. Its light peaks at about 1 millimeter in the microwave band. Radio telescopes map it in exquisite detail. Human eyes have never registered a single photon of it. It fills every cubic centimeter of space, including the space between your hands right now. Fly into it at 99% of light speed, and it blue shifts along with everything else. From 2.7 Kelvin to about 38 Kelvin, its peak sliding from 1 millimeter to roughly 75 microns. Now, popular accounts often claim that this makes the Big Bang's afterglow visible to the naked eye. Let's be precise, because the real answer is more interesting than the myth. 75 microns is still far infrared, still invisible. At 99% of light speed, the oldest light in the universe remains something only an instrument could detect, but its energy density in the forward direction has risen by roughly 40,000 times, and pushed the speed further to around 99.99% and beyond, and it genuinely does climb into visible wavelengths and then past them. 4 physics students at the University of Leicester ran exactly this calculation in 2013 for the Millennium Falcon's jump to light speed, publishing it in their department's Journal of Physics Special Topics. Their conclusion: no star streaks, a bright disk dead ahead, made of the afterglow of the Big Bang, and a hard dose of X-rays with it. Fiction, obviously. The optics are not. So compose the whole image. Imagine standing at that forward viewport at 99% of light speed. Ahead of you, a tight, brilliant ring of concentrated light, almost the entire sky folded into a circle you could cover with an outstretched hand. Its colours are wrong in a way you cannot correct for, because you are seeing the infrared underside of stars whose true visible faces have shifted somewhere your eyes cannot follow. Scattered through it are objects too cold to have ever appeared in any human night sky. Turn your head, and there is nothing. Not dimness. Blackness in every direction except forward. And beyond that ring, invisible but measurably present, the compressed heat of the beginning of time. No streaks, no motion, just a still, silent, blazing eye in the middle of the dark, and it does not move because you are travelling directly into it, which raises a question researchers have not settled. Is that forward radiation merely something to look at, or something that can kill you? One camp treats it as a serious engineering problem. Analyses of relativistic flight, including work by Thiem Huang and colleagues on the heating of relativistic spacecraft, treat forward-shifted photons and particles as a genuine thermal and shielding burden on the leading surface, requiring the ship to dump that heat or cook from the front inward. Anything you fly toward a star at these speeds meets that star's light hardened into something far more penetrating than light. The other camp runs the photon numbers and finds them small. One analysis of relativistic intergalactic flight calculates that even at a Lorentz factor of 1,000,000, a speed so extreme it makes 99% look like standing still, the pressure of the blue-shifted background comes to about a 10,000,000th of a Pascal, negligible next to the pressure from matter, and the point where background photons become capable of producing electron-positron pairs inside the hull requires a Lorentz factor of order 100 million. So both sides may be right about different regimes, and the disagreement is really about where the line sits. The stakes are practical, whether the forward shield of any real starship must be built to stop radiation or only to stop matter. That question stays open. Set aside the danger for a moment and consider a quieter cost. Every constellation would be gone, not obscured, dismantled. Orion, the Southern Cross, the Plough, their stars swept into that forward cone, their colours reassigned, their geometry destroyed by aberration that varies with your exact speed. Think about what that actually removes. For as long as human beings have existed, we have looked up and known where we were. Polynesian navigators crossed thousands of miles of open Pacific by star path. Sailors found latitude from the pole star. Migrating birds, sea turtles, dung beetles. The sky is one of the oldest orientation systems life on this planet has. A relativistic crew would be the first humans in history to look out and find it unusable. Not obscured by cloud, genuinely, permanently rewritten. And the instruments face the same problem. in reverse. A telescope designed for visible light would be pointed forward into a sky whose visible light has become ultraviolet. It would be looking at the wrong rungs of the ladder entirely. Every optical system on that ship would have to be built for the wavelengths that arrive, not the ones that left. Everything the crew could see would have to be reconstructed from mathematics before it meant anything at all. And here's the thing worth holding on to. Everything described so far, the burning ring, the missing constellations, the darkness astern, the invisible ancient glow, is made entirely of photons, massless, weightless, nothing more than light arriving at strange angles in strange colours. The window shows you a rewritten sky, but the same space carrying that light is also carrying something else. Atoms, grains of dust, ordinary, unremarkable specks of matter drifting between the stars at a few kilometres per second, doing nothing to anyone. Fly into them at 99% of light speed, and they stop being specks. Almost everyone believes interstellar space is empty. Not sparse, not thin. Empty, a perfect nothing between the stars, a clean vacuum a ship could sail through without touching anything at all. That belief is wrong, and the error turns out to be one of the most dangerous in the entire subject. Across the galaxy as a whole, the space between stars holds roughly 1 atom per cubic centimetre. Picture a sugar cube. Somewhere inside that volume, drifting, a single atom. That's the average. About 90% of those atoms are hydrogen, the simplest thing the universe makes. Around 10% are helium. And threaded through the rest, in tiny fractions, sit the heavier elements: carbon, oxygen, nitrogen, and traces of iron, forged inside dead stars and scattered when they collapsed. Then there is dust, not household dust, grains of silicate rock and carbon, most of them 1/10 of a micrometer across. 1,000 of them lined up would span the width of a human hair. Now here's the perspective flip most people find hardest to accept. Human beings have spent decades chasing the perfect vacuum. Inside the beam pipe of CERN's Large Hadron Collider, one of the emptiest volumes ever engineered on Earth, pumped down to around a 10/1000th of atmospheric pressure, you would still find something like a few million molecules in every cubic centimetre. A few million. Against interstellar space's 1. The best vacuum we know how to make is millions of times denser than the space between the stars. Every intuition we have about nothing was formed inside a laboratory that is, by cosmic standards, thick with matter. So interstellar space really is astonishingly empty. It is just not empty enough. Before going further, an honest complication, because the number we just used is a galactic average, and averages hide things. Voyager 1's plasma wave instrument made the first direct measurement from outside the heliosphere. In October 2013, at 122.6 astronomical units, it recorded an electron density of about 0.055 per cubic centimetre. Later readings came in near 0.08. Voyager 2, crossing in a different direction, measured about 0.039 per cubic centimetre in January 2019. Those are electrons rather than total atoms, so the two figures are not directly interchangeable. But the picture they build is consistent. The Sun currently sits inside a region called the local interstellar cloud, and that cloud appears thinner than the textbook galactic average, and it isn't smooth. Work led by Stella Ocker at Cornell, using Voyager 1's persistent plasma wave signal, revealed a large-scale density gradient and genuine turbulence out there. The medium has structure, thicker patches, thinner patches, currents in something we assumed was still, which produces a problem nobody can solve from here. Every hazard estimate for a starship depends entirely on which clouds its specific route crosses. A probe aimed at Alpha Centauri would have to pass out of our local interstellar cloud and into the neighbouring G cloud, and no instrument has ever sampled that boundary. We are planning a crossing without knowing the depth of the water. Now, a reasonable objection. Voyager 1 has been flying through this material for over a decade, And it's fine, perfectly true. At 38,000 miles per hour, 61,000 kilometers per hour, a hydrogen atom striking the hull deposits an amount of energy so small that nothing registers it. Voyager is drifting through a fog so thin it may as well not exist. The medium hasn't changed, the speed has. Push to 10% of light speed, and every one of those hydrogen atoms arrives carrying about 4.7 million electron volts. That number needs a translation, so here's one you can hold. 4.7 million electron volts is close to the energy of an alpha particle thrown out by decaying radium, the kind of particle a Geiger counter clicks for. Every hydrogen atom in your path becomes a radiation event, and they don't arrive one at a time. At 10% of light speed, every square centimetre of forward-facing hull, an area smaller than a postage stamp, absorbs roughly 3 billion of them every second. Push to 90%, and each atom carries more than 1,200 million electron volts. That is genuine cosmic ray energy, the kind physicists build kilometre-scale machines to produce. So let's reframe what this ship actually is. Not a vehicle flying through thin gas. A vehicle flying nose first into a particle accelerator beam, one with a low density but an enormous cross-section, aimed permanently at the front of the craft, that cannot be switched off until you decelerate. Nobody built that beam. You built it by moving. In 2017, 4 researchers, Thiem Hoang, Alex Lazarian, Blakesley Burkhart and Abraham Loeb, published the first serious quantification of this in the Astrophysical Journal, modelling exactly what Breakthrough Starshot's gram-scale craft would suffer at 20% of light speed. Their finding was not what most people expect. The hydrogen isn't the main problem for the material itself. The rare heavy atoms are. When an iron or oxygen nucleus arrives at relativistic speed, it dumps energy so densely along its path that it melts a channel a few nanometers wide straight into the solid, a permanent scar physicists call a damage track. Picture a needle drawn through wax, except the needle is an atom and the wax reseals into something structurally different. Across the full path to Alpha Centauri, their model predicted damage to a depth of roughly 0.1 millimeters in quartz. The thickness of a sheet of paper, but a sheet of paper of ruined surface across everything facing forward, on a craft designed to weigh a few grams. Then came the result that changes the engineering. Graphite performed dramatically better than quartz under the same bombardment, which means the survival question is not simply how thick to build the shield. What you build it out of matters more. Except the story does not end there, and this is where the science gets genuinely unsettled. Marko Karlušić at the Ruđer Bošković Institute in Zagreb published a direct comment on that paper. His objection is technical but consequential. The team used the SEANS analytical thermal spike model to predict track formation, and Karlušić argues they applied it incorrectly by neglecting what materials physicists call the velocity effect. The effect is real and strange. 2 ions can deposit identical energy per unit distance while travelling at very different speeds, and for reasons still under debate, slow ions form tracks far more easily than fast ones. So using laboratory data from slow ion irradiation of quartz to predict damage from relativistic iron nuclei may simply be the wrong comparison. His conclusion is careful rather than dismissive. Redo the calculation properly, he argues, and only then can anyone say whether the original ranking of gas versus dust as the dominant threat still holds. Nobody has settled it, and later work has added a mechanism neither side originally modelled. Relativistic hydrogen and helium penetrate to similar depths and then stop, accumulating below the surface as trapped gas, the same process that plagues the plasma-facing components inside fusion reactors, where implanted gas gathers into bubbles and blisters the material from within. Think of moisture sealed under a coat of paint, slowly lifting it from underneath. Now imagine it happening across the entire leading face of your ship for decades, with no way to inspect it. The gas is the constant background, the dust is the event. A typical interstellar grain, 1/10 of a micrometer across, weighs around 10 femtograms, roughly 100 trillionth of a gram, utterly harmless in any ordinary context. At 20% of light speed, That single grain carries about 23 thousandths of a joule, comparable to a small pebble tossed gently underhand. But the total energy is not what matters here. The concentration is. All of that arrives inside a region a fraction of a micrometer wide in a few femtoseconds, and a femtosecond is a millionth of a billionth of a second. The time light needs to cross about a third of a bacterium. At that energy density, ordinary material physics stops applying. The grain does not dent the hull, and the hull does not stop the grain. Both of them, grain and impact site together, flash instantly into plasma, a microscopic explosion that blows a crater out of the surface. Now, scale up to the rare case. Most grains are vanishingly small, but larger particles exist, and across trillions of miles of path you will eventually meet one. Take a grain of fine sand, 1 milligram, a little under a millimeter across. At 10% of light speed, it carries the energy of about 108 kilograms of TNT. At 20%, roughly 440 kilograms. At half the speed of light, more than 3,300 kilograms, 3¼ tons of high explosive, the energy released by burning around 400 litres of petrol, about 8 full car tanks. All of it delivered into a spot smaller than a pinhead, in less time than it takes light to cross a human cell. We already know how to protect spacecraft from high-speed impacts. Fred Whipple worked out the principle in 1947, and the International Space Station carries his design today, a thin outer bumper spaced away from the hull. A striking particle doesn't punch through the bumper, it shatters against it, spreading into a diffuse cloud of fragments that the rear wall can absorb. Whipple shields work beautifully at orbital speeds, around 10 kilometers per second, 6 miles per second. At relativistic velocity, the physics changes completely. The particle does not shatter on the bumper, it ionizes straight through it, depositing energy along a line and continuing as a spike of plasma into whatever sits behind. The bumper does not spread the threat, it becomes part of it. Magnetic deflection has the same problem. A magnetic field can push charged particles aside, and some of the incoming hydrogen is ionized, so a magnetic shield helps. But much of the local hydrogen is electrically neutral. A magnetic field passes straight through it, as if it weren't there, and no realistic field bends a milligram of rock. Material choice offers real leverage. Hydrogen-rich substances, water, polyethylene, break up incoming particles more cleanly and generate fewer secondary particles than aluminium or iron. And that word, secondary, carries the trap. A thin aluminium shield can actually increase the radiation dose inside. One high-energy particle enters, strikes a heavy nucleus, and a shower of new particles sprays out the other side. One in, many out. Put a screen door in front of a sandblaster, and you haven't stopped the sand. You have turned it into shrapnel. To genuinely suppress that cascade, the shielding conversation stops being about centimeters and becomes about meters. Meters of anything means mass, and mass is precisely what the energy equations punish hardest. One final number, and it belongs to the vessel rather than the void. A 1,000 kilogram spacecraft, lighter than a family car, traveling at 10% of light speed carries kinetic energy equivalent to about 108 megatons of TNT. The largest nuclear device ever detonated, the Tsar bomber tested in 1961, released roughly 50 megatons. So the ship is carrying more than twice that continuously for the entire voyage, and its single non-negotiable job is to never release it, which reshapes the whole design philosophy. The goal stops being strength and becomes something engineers call graceful degradation, allowing the vehicle to erode, blister, pit, and scar without ever failing in a way that sheds fragments. Because a piece that breaks off at these speeds does not simply fall away. It becomes another projectile traveling alongside you with the energy of a bomb. A cracked panel is not a repair job. It is a loaded weapon in formation. And here's the honest summary of everything the Void does to a ship. All of it is engineering. Hard engineering, unfinished engineering. Engineering built on models that specialists are still arguing about, but engineering nonetheless. Choose graphite over quartz, add mass, reshape the leading edge, accept erosion, trade payload for shielding and shielding for speed. Every one of these problems has a direction you could push in, given enough resources and enough decades. The hull can be designed for this, but the hull exists to protect something that cannot be redesigned at all, something that evolved over 4 billion years for exactly one set of conditions, on exactly one planet, and which begins failing the moment you take it away from them. The next problem isn't the ship, it's the body inside it. Consider what your body is actually calibrated against. Right now, without you noticing, 1 g of gravity pulling every bone and muscle downward, all day, every day, for your entire life. Roughly 1 kilogram of air pressing on every square centimetre of your skin, about 15 pounds per square inch. The weight of an atmosphere dozens of miles deep standing on your shoulders. A planetary magnetic field deflecting most of the charged particles the sun throws at us. And a filter of air so thick that only a small fraction of cosmic radiation ever reaches the ground. 4 billion years of evolution tuned a machine to those exact settings. Now here's the framing that matters most, and the one almost every account gets wrong. When you take that machine into space, the body does not break down. The body adapts, beautifully, efficiently, exactly as designed. That's the problem. Adaptation is not improvement. Adaptation is optimization for whatever environment you actually occupy. And a body that is optimized for weightlessness has become superbly suited to a place that will eventually kill it. Bone feels permanent. It isn't. Bone is living tissue, torn down and rebuilt continuously by 2 populations of cells. Osteoblasts lay new material down. Osteoclasts dissolve old material away. Mechanical loading, walking, standing, carrying, tells the system where to keep building. Picture a road crew that repaves only the routes where traffic actually runs and quietly lets unused roads crumble. That's your skeleton every day of your life. Remove the load and the crew stops resurfacing. Astronauts lose roughly 1 to 2% of bone mineral density every month, concentrated in the load-bearing structures, hips, spine, legs, over a standard 6-month mission that accumulates to something like 10 to 15%. But the loss is not the finding that should worry us. The recovery is. In 2022, Lee Gable and Stephen Boyd's team at the University of Calgary published results in scientific reports from 17 astronauts, 14 men, 3 women, average age 47. They scanned the shin bone and forearm before flight, on return, and again at 6 and 12 months, using imaging fine enough to resolve individual internal struts of bone. A full year after landing, median shin bone strength and density remained measurably below pre-flight values. Astronauts who had flown longer than 6 months recovered worst, their bone strength still down almost 4%. 9 of the 17 had not fully recovered shin bone density at all. Gable's own framing of the result is the one that lands hardest. The sustained loss is roughly equivalent to a decade or more of normal age-related bone loss on Earth. 6 months in orbit, 10 years off the skeleton, except the story may not be finished. In 2025, the same Calgary group published a case study in MPJ microgravity, following 2 crew members all the way out to 4 years. One had recovered completely. The other still carried deficits in the internal lattice of the bone, but had compensated by thickening the outer shell. So permanence remains genuinely unsettled. Remodeling slows sharply after the first year, but whether it truly stops, nobody yet knows. One encouraging signal ran through both studies. Astronauts who did more resistance training in flight, particularly deadlifting, recovered better. Load, it turns out, is the message the skeleton is listening for. Muscle follows the same logic and fails faster. Crew aboard the International Space Station exercise roughly 2.5 hours a day, 6 days a week. Treadmill, cycle, resistance machine. Not as recreation, but as a medical prescription. That routine is the most aggressive countermeasure program ever run in the history of medicine, and NASA reports muscle mass losses of up to 20%, even on relatively short flights. Let that sit for a moment. 2.5 hours daily of mandatory monitored training, and the body still disassembles a fifth of the machinery it isn't using. Exercise slows atrophy. Nothing demonstrated so far actually stops it. Meanwhile, the cardiovascular system is being quietly rewritten. On Earth, your heart fights gravity constantly to push blood upward. Remove gravity, and fluid that normally pools in the legs migrates into the chest and head. Astronauts describe it plainly. Puffy face, thin legs, a permanent head cold sensation. The body senses that chest fullness and concludes it has too much blood. So, it sheds volume. And with less blood to move and no gravity to fight, the heart does less work and does what any underused muscle does. It remodels smaller, perfectly rational, exactly correct for microgravity, catastrophically wrong for coming home. Crew returning from 6 months arrive with reduced blood volume and a heart no longer strong enough for a standing world. Many experience orthostatic intolerance, blood pressure collapsing when upright. They faint. They are lifted out of the capsule and carried to medical chairs, not because they are injured, but because their circulation no longer works in gravity. And now, the number that reframes everything above, the longest continuous spaceflight any human has ever completed, belongs to the Russian physician Valery Polyakov, who spent 437 days aboard Mir between January 1994 and March 1995. 14 months. A 10-year voyage would exceed the entire span of human experience by more than 8-fold. Every physiological number we have is an extrapolation off the end of a very short chart. Then there is the effect nobody predicted and nobody has yet explained. Somewhere between roughly half and 70% of long-duration crew, the figure varies by study and by how strictly you define it, develop something called spaceflight-associated neuroocular syndrome. The back of the eyeball flattens, the optic disc swells, folds appear in the tissue layers behind the retina. Vision shifts toward farsightedness, and in some cases the changes have not fully resolved after returning to Earth. NASA classifies it as a red risk, high likelihood, high consequence. Now, the obvious explanation is fluid pressure inside the skull. Headward shift raises intracranial pressure. That pressure transmits along the sheath around the optic nerve, and the eye deforms, except the evidence refuses to cooperate. Astronauts with these changes generally lack the classic signs of raised intracranial pressure. No severe headaches, no pulsatile ringing in the ears, no transient blackouts of vision, and spinal fluid pressures measured after landing come back normal or only mildly elevated. So researchers are working several competing explanations at once. Perhaps the pressure isn't global but compartmentalized, trapped locally within the optic nerve sheath. Perhaps the real driver is venous congestion, with blood unable to drain properly from the head. Perhaps the brain's lymphatic system, its waste clearance plumbing, which appears to depend on posture and sleep, simply stops working correctly without gravity. None of these has won. The mechanism remains open, and the operational stakes are severe because the eyes are the interface for everything: reading an instrument display, assessing a wound, performing a delicate repair on a system nobody can replace. A crew years from any help cannot afford deteriorating vision, and cannot afford a countermeasure designed against the wrong cause. Something else weakens quietly in the background. Immune cell function becomes impaired in spaceflight. The proliferation of certain cells slows, signaling shifts, and with that loosened control, viruses your body has been holding down silently since childhood begin waking up. Satish Mehta, Brian Crucian and colleagues tracked 23 astronauts before, during and after long missions. 8 of them shed reactivated virus: Epstein-Barr, varicella zoster, cytomegalovirus. Compared with short shuttle flights, reactivation on long missions occurred more often, lasted longer, and reached higher viral copy numbers. Usually the astronauts felt nothing, but saliva samples taken days after landing contained live, infectious virus. Chickenpox never leaves. It hides in nerve tissue for decades, restrained by immune surveillance. Weaken that surveillance for years, in a sealed metal volume shared by a handful of people, and the arithmetic changes. Now the hardest constraint, and this one comes from measurement rather than modelling. When NASA's Curiosity rover flew to Mars, it carried an instrument called RAD, the Radiation Assessment Detector, mounted inside the spacecraft, where a crew would sit. During the cruise, it recorded an average dose equivalent of 1.8 millisieverts per day. Translate that, roughly 660 millisieverts a year, against a natural background on Earth of a few millisieverts annually. The team calculated that the transit phases alone of a Mars round trip would deliver approximately 0.66 sieverts. Set that against the rule. NASA's 2022 radiation standard caps career exposure at 600 millisieverts, a single universal limit, applied regardless of age or sex. Divide one into the other, and the mission planning collapses. An astronaut's entire career radiation allowance, everything they are permitted to absorb across a working lifetime, is spent in roughly 330 days of interplanetary cruise. 11 months. Not 11 months at Mars. 11 months of simply travelling, and the limit itself is contested. Francis Cucinotta, who spent years as NASA's lead scientist on space radiation, has argued repeatedly that the risk numbers do not close, that Mars-class missions sit at or beyond defensible exposure, and that the uncertainties in the underlying cancer risk estimates are wide enough to make any single threshold questionable. Others counter that a universal limit is a reasonable, transparent risk judgment rather than a physical boundary, and that standards for deep space may legitimately differ from standards written for low Earth orbit. Nobody has settled where the line belongs, but every version of the argument agrees on one thing: the clock runs fast. Here's what makes this radiation unlike anything in medicine. An X-ray deposits energy diffusely, a little everywhere, like sunlight falling on skin. Galactic cosmic rays include heavy nuclei, iron most notoriously, travelling at enormous energy. When one of those passes through tissue, it does not spread its damage. It cuts a track. A single iron nucleus draws a line through the body, severing the long fibres that carry nerve signals, stripping the insulating myelin around them, killing cells along its path. Not a dose, a wound, microscopic and linear, and there are many of them, every day, for years. So what does that do to a brain? Rodent studies have produced genuinely alarming answers. Work from Charles Limoli's group and others found persistent impairments in spatial memory, recognition memory, and executive function months after exposure, alongside measurable loss of dendritic complexity, the branching structures neurons use to connect. A 2023 study in Nature Communications, using a 33-beam simulation of the real cosmic ray spectrum, again found cognitive and neurochemical decrements in exposed mice. But that is not the whole literature. Also in 2023, Victor Kokan and Mikhail Dobinde published a review in the journal Biology Analyzing Studies of flight-relevant doses across development, emotional state, cognition, neurogenesis, and neurodegeneration. Their conclusion ran the other way, that cosmic rays appear relatively safe for central nervous system function, and that under some exposure scenarios, irradiated rodents and non-human primates actually performed better on cognitive tasks, though often alongside hyperactivity and anxiety. Both bodies of work are real. The weak link both share is the same: extrapolating from a mouse brain, irradiated over minutes on Earth, to a human brain absorbing a thin, continuous drizzle over years. And the reason the argument matters is uncomfortable. The functions under question, memory, judgment, decision-making under stress, are precisely the ones keeping everyone aboard alive. Set every one of those aside for a moment, because something more basic is missing from most discussions of interstellar travel. No fully closed life support system has ever operated at human scale. Not once. The International Space Station recycles most of its water, and that is a genuine engineering triumph. but it grows no meaningful food, and a resupply vehicle arrives every few months. The station is not a closed loop. It is an open system with a very long umbilical. The closest anyone came was Biosphere 2, 8 people sealed inside a 3-acre glass structure in the Arizona desert in 1991, with a farm, a rainforest, an ocean, and a mangrove swamp. The oxygen started disappearing. Over the first 16 months, oxygen fell from 20.9% to about 14%, roughly what you would breathe at 15,000 feet, around 4,500 meters. Half the crew developed symptoms of altitude sickness, including sleep apnea, fatigue, trouble concentrating, and nobody could find where it had gone. Falling oxygen should have meant rising carbon dioxide, but the carbon dioxide wasn't accumulating. Researchers eventually traced it. Microbes in the over-rich soil were consuming the oxygen, and the building's own concrete was absorbing the carbon dioxide they produced, erasing the evidence as fast as it appeared. They pumped in liquid oxygen from outside. The seal broke, and with it the premise. Study that failure closely, and the lesson is not that the science was bad. The lesson is the shape of it. Slow, invisible, chemical, hidden inside the structure itself, and discovered only when people started struggling to think clearly. Those people were standing 30 feet from a door. One idea keeps returning as the possible answer to all of it. Don't keep the body awake. Both major agencies are taking it seriously. The European Space Agency ran a study called MICRA, assessing systematically what controlled torpor, the reduced metabolism state of hibernating mammals, would demand and deliver. NASA is developing STASH, a facility for studying torpor in animals aboard the space station. The appeal is enormous. Lower metabolism means dramatically less food, water and oxygen, less muscle and bone wasted through disuse, and, remarkably, experiments have shown synthetic torpor to be genuinely radioprotective, even in animals that don't naturally hibernate. But let's be honest about where it stands. Deep metabolic suppression in humans is, right now, impossible. Researchers cannot do it, and the mechanisms remain incompletely understood. What looks achievable in the near term is shallow, a depression of metabolic rate of around 20%, induced through enhanced slow-wave sleep and moderate sedation. Helpful, not transformative. Not yet. So here is the honest ledger. Bone, muscle, heart, eyes, immunity, radiation, air and food. Every one of them has a direction to push in. Spin the habitat for gravity, add shielding mass, develop drugs, refine the closed loop, pursue torpor. None of it is solved, but all of it is the kind of problem that money, time and mass can move. Keeping a human body alive across a decade is solvable on paper. But there is one passenger aboard that no centrifuge spins, no shield protects, no exercise routine maintains, and no torpor protocol has been shown to preserve. And it begins to suffer long before the bones do, because of something that starts happening the moment the ship pulls away and never stops getting worse. We already have data on what happens to a human mind sealed inside a small volume with no way out. Not speculation, decades of it, gathered in the coldest places on this planet and under its oceans. The closest analogue sits on the Antarctic Plateau, Concordia Station, where crews spend a full year, including 4 months of continuous darkness and a winter during which no aircraft can reach them. The European Space Agency funds research there precisely because nothing else on Earth comes closer to a long-duration mission. Antarctic winter-over research, running back to the 1970s, keeps finding the same cluster of effects, so consistently that psychiatrists gave it a name: winter-over syndrome, depressed mood, hostility, disturbed sleep, impaired cognition. Observers documented something stranger too. They called it the Antarctic stare, or long eye, a person sitting motionless, eyes open, mentally blank, not asleep, not thinking, simply absent. And in 1991, Robert Bechtel and Amy Burning described what became known as the third quarter phenomenon, a dip in mood and cooperation appearing around 3/4 of the way through a stay, seemingly independent of how long the stay actually is. The trigger appears to be expectation rather than the calendar. The moment when the halfway point has passed but the end still feels unreachable. Let's be honest about the strength of that finding. Some expeditions show it clearly, others don't. The evidence remains genuinely mixed. But the physical evidence is not mixed at all. In 2025, researchers published a study in NPJ microgravity that went further than mood questionnaires. 25 Concordia crew members received MRI brain scans before their 12-month stay, immediately after, and again 5 months later. The scans showed measurable decreases in grey matter across the temporal and parietal lobes, the hippocampus, the thalamus, alongside a reduction in white matter and an enlargement of the brain's fluid-filled ventricles. Most of it returned to baseline within 5 months of coming home, and one relationship stood out clearly in the data. Crew members who slept better lost less brain volume. The mind is not merely uncomfortable in isolation, the organ measurably changes shape. Add to this the finding every study of small confined groups reproduces. Conflict concentrates. In a crew with no exit, no alternative company and no possibility of walking away, ordinary friction has nowhere to dissipate. It compounds. Now here's what makes interstellar isolation categorically different from every analogue we have. At Concordia, the crew can call home, not in person, but in near real time. Voices arriving as they are spoken. A submarine patrol has a fixed end date printed on a schedule. The International Space Station orbits 90 minutes from the ground, in constant contact, with a return vehicle permanently docked. Every one of those environments holds one thing steady: the link. An interstellar voyage has a property none of them share. The connection does not merely stretch, it degrades continuously, every single day, and never improves until the ship turns around. Think about what that actually means. On day one, you can hold a conversation. 6 months later, you cannot. And nothing you do, and nothing anyone at home does, can reverse it, because the distance is the cause, and the distance is the mission. Let's follow it outward, because the ladder is arithmetic rather than opinion. Light itself sets the pace, and nothing carries a message faster. At 1/10 of a light year, a signal takes about 36 days to reach Earth, 10 weeks for a full exchange. Send, wait, receive. Workable in the way ocean correspondence was workable in the 1700s. A ship's captain wrote home, and an answer came the following season. At 1/4 of a light year, 3 months each way, half a year for a single round trip. And here something real breaks. Mission control can no longer advise, not slowly, at all. Every message becomes a report on something already finished. At half a light year, 6 months each way, a full year per exchange. What passes between ship and Earth stops being conversation and becomes archive. Records deposited, not dialogue held. At 1 full light year, a message takes a year to arrive. A reply takes another. 2 years, minimum, for a single loop. So imagine a genuine crisis aboard. A medical emergency nobody on the ship knows how to treat. They describe symptoms carefully, transmit, and wait. 2 years later, guidance arrives from the best specialist on Earth, accurate, thorough, and addressed to a situation that resolved itself, one way or the other, 23 months ago. The advice is not late. The advice is archaeological. Now place yourself inside that gap, because this is the part that stops being engineering. You sit down to write to someone you love. You tell them what happened this week, the argument, the small triumph, the thing you can't stop thinking about. You send it. A year passes. They read it, and they answer honestly and tenderly, responding to a person who existed 12 months ago. They ask how you're feeling about something you resolved and forgot. They offer comfort for a fear you no longer have. Another year passes. Their reply reaches you. You are now reading a letter written by someone who is already a year further into their own life than the words in front of you. Someone who has had a birthday, changed their mind, possibly grieved someone you don't yet know is gone. Both of you are corresponding with people who no longer exist. Not because either one has stopped caring. The care is completely real, and it arrives intact. but because the shared present tense has quietly stopped overlapping. You do not lose the relationship, you lose the word meanwhile. Except one genuine improvement exists, and most accounts of interstellar travel skip it entirely. In 1979, the Stanford physicist von Eschleman published a paper in Science pointing out something remarkable about our own star. Mass bends light, the effect Arthur Eddington measured during the eclipse of 1919. And the sun bends light so predictably that it works as a lens, focusing radiation from anything directly behind it. That focus is not a point, it's a line, beginning around 550 astronomical units from the sun and continuing outward. Put a relay probe on that line and something extraordinary happens. The sun becomes your antenna, an antenna the diameter of a star. The gain runs to many orders of magnitude. Claudio Marconi's analyses for the focal mission concept found that a transmission which would be pure noise if sent directly could arrive essentially error-free across several light-years using the lens on modest power. Slava Turashev's team at NASA's Jet Propulsion Laboratory has been developing the mission architecture under NASA's Advanced Concepts program, established physics, not fantasy. But let's be honest about the difficulties, because they're severe. The focal region where the amplification works is only meters across, so the probe must hold its position with extraordinary precision, and plasma in the sun's outer atmosphere scatters lower frequency signals, a critique Turashev himself co-authored in 2003, pushing the usable focus further out for some wavelengths, and the probe would need to reach 550 astronomical units, more than 3 times farther than Voyager 1 has travelled in nearly half a century. Now the part that matters most, and the reason the lens does not rescue the crew. Gravitational focusing amplifies the signal. It does not accelerate it. A perfectly clear message still takes a year to cross a light year. The lens fixes the whisper. Nothing fixes the wait. Which brings us to a problem that sounds harder than it is. Every star chart you have ever seen is a lie of convenience. Nothing in it is fixed. Our own sun orbits the centre of the Milky Way at roughly 230 kilometers per second, about 514,000 miles per hour. Fast enough to cross the entire Earth in under 3 minutes, and it has been doing it your whole life without you feeling a thing. One full circuit takes somewhere near 225 million years. The last time the sun occupied this position in the galaxy, the first dinosaurs were appearing on a planet whose continents were still fused into one landmass. And every target star is doing the same thing, on its own path, at its own speed, in its own direction. So you cannot aim at where a star appears. You must aim at where it will be when you arrive, decades or centuries downstream. Remarkably, we can already do this. The European Space Agency's Gaia mission has measured positions, motions and distances for roughly 1.8 billion stars. Not photographed, precisely measured, including how each one drifts across the sky. For anything within 100 light years, those predictions are accurate enough to plot and intercept many years ahead. On board, one more correction runs continuously, because the apparent geometry of the sky shifts with the ship's instantaneous velocity. The target star is never quite where the window shows it. Aberration corrections would have to be computed in real time, all the time, updating with every change in speed. And for absolute position, knowing where you actually are with no landmarks, nature has already provided the answer. Millisecond pulsars are collapsed stellar cores, spinning hundreds of times a second, sweeping beams of radiation past us like lighthouses. Their timing rivals atomic clocks. The arrival of their pulses can be predicted to within microseconds, years into the future, which makes them a positioning system that covers the galaxy and requires no infrastructure at all. NASA tested exactly that. In November 2017, an experiment called Sextant, running on the NICA X-ray telescope aboard the International Space Station, selected 4 millisecond pulsars, timed their X-ray pulses, and fed the arrival times into onboard software. Within 7.5 hours, the system had located itself in orbit to better than 10 kilometers, about 6 miles, completely autonomously, without a single signal from the ground. A working galactic positioning system, already demonstrated, already flown. So here's the verdict, and it is the one genuinely encouraging finding in this entire story. Navigation is the most tractable problem we have. Knowing where you are and where you're going was never going to be what stopped us. 2 other questions are far less settled. The first sounds simple and turns out to be wide open. What is the minimum crew that can survive a multi-generational voyage without collapsing genetically? Frédéric Marin and Camille Bellouffi built a Monte Carlo simulation called Heritage to run the question properly, testing thousands of randomized scenarios of birth, death, pairing, and infertility. Their answer for a 6,300-year voyage to Proxima b, 98 people to guarantee a healthy arriving population. Below about 32, their simulations showed the success rate falling to 0, inbreeding making failure inevitable. Others land somewhere entirely different. Moore's 2003 analysis proposed 150 to 180. The anthropologist Cameron Smith in 2014 argued for 14,000. Marin's later work, once genetic parameters like mutation and drift were included, suggested 100 to 500 at departure. More recent modelling using fluctuating anthropological parameters produced a range of 1,400 to 6,800. The disagreement is not sloppiness. Each model makes different assumptions about infertility rates, family size, catastrophe margin, and how much genetic diversity a founding population truly needs. But look at what the spread means practically. The difference between 98 people and 14,000 is a factor of more than 100 in food, air, water, volume, and above all, in mass. Nobody can design the ship until that argument ends. The second unresolved question is stranger, and it comes down to the inner ear. The only workable way to make gravity aboard a ship is rotation. Spin the habitat, and the floor pushes up against you, exactly like a fairground ride pressing you outward. The trouble is what spinning does to the balance organs in your head. Turn your head inside a rotating structure, and the fluid in your inner ear receives signals it was never built to interpret. The result is nausea. Old comfort studies from the 1960s set the safe limit at about 2 rotations per minute. Run that number, and the ship becomes monstrous. At 2 revolutions per minute, generating 1 full G requires a radius of roughly 224 meters, about 735 feet. That means a rotating wheel 450 meters across, taller than the Empire State Building, spinning continuously in deep space. Except Al Globus and Theodore Hall have argued for years that those old limits were far too conservative, that 4 rotations per minute is tolerable, which brings the required radius down to just 56 meters, about 184 feet, a structure roughly the length of a football pitch instead of a skyscraper, and the experimental data pushes harder still. Lawrence Young's team at MIT showed in 2001 that most subjects on a 2-meter centrifuge adapted their reflexes while rotating at 23 revolutions per minute. Later, MIT work examined incremental adaptation at 30. Nobody has resolved it, and the reason is honest. Adapting for hours in a laboratory with a scheduled end is not the same as living inside rotation for a decade, sleeping in it, working in it, raising children who have never known anything else. That experiment has never been run and cannot be run on Earth. Now watch how far that unresolved question reaches. If humans can tolerate faster spin, the habitat radius collapses. Smaller radius means dramatically less structure. Less structure means less mass. And less mass feeds straight back into the energy equations, the ones that already demanded centuries of planetary electricity output. A question about the fluid in the human inner ear turns out to be a propulsion question, which is the pattern running through all of it. Every countermeasure, shielding, spin, food, water, redundancy, crew size, adds mass. And mass is precisely what the physics punishes hardest. So the ledger is complete as far as anyone can complete it. The ship can be built, in principle, with materials we have not yet chosen, and an engine that does not yet exist. The body can be kept alive, imperfectly, with countermeasures that slow rather than stop the damage. The mind can be supported, with better sleep, better design, better crew selection, and a relay probe at the sun's gravitational focus, keeping the whisper audible across a widening dark. And the navigation is genuinely, remarkably solved. Everything has been counted, every cost identified, every unknown named. Now there is only one thing left to do with all of it: arrive. The engines stop. Whatever burned to get here has finished burning, the deceleration is complete, and the ship holds position exactly 1 light-year from the sun, 5.88 trillion miles, 9.46 trillion kilometers. Everything paid. Look around. Nothing. No planet. No moon. No atmosphere. No magnetic field. No surface to stand on. No body to orbit. No landmark of any kind in any direction. The nearest star system, Proxima Centauri, still lies more than 3 light-years further on, 3/4 of the journey to our closest neighbour still ahead, after a crossing that consumed everything a civilization could give it. This is not an arrival. This is a position. Sunlight reaches this place, but calling it light stretches the word past usefulness. At Earth's distance, the sun delivers about 1,361 watts to every square metre, enough to warm your skin, dry a road, run a rooftop panel. Out here, that same square metre receives roughly a 4/billionth of it, about 3/10,000,000ths of a watt. Translate that into something you could hold. A solar panel that produces a few hundred watts per square metre in Earth orbit would generate, at this distance, something near 70/billionths of a watt. To run a single 5-watt reading lamp, you would need an array of roughly 73 square kilometres, about 28 square miles, larger than the entire island of Manhattan, an array bigger than a city to light one bulb. So sunlight has stopped being a resource and become a memory. Every watt of warmth inside that hull is generated aboard, by the crew's own bodies, by the electronics, by whatever reactor is still running. The sun contributes nothing at all, which creates a difficulty that sounds backwards until you think it through. Out here, in the deepest cold anyone has ever occupied, the ship's most serious thermal problem is overheating. On Earth, heat leaves things 3 ways. Conduction carries it into whatever you're touching, convection carries it away in moving air or water, and radiation carries it off as infrared light. In vacuum, the first 2 simply do not exist. Nothing touches the ship. No air surrounds it. Think of a thermos flask. The reason it keeps coffee hot is not insulation in the ordinary sense. It's the vacuum layer sealed inside the wall, which blocks conduction and convection completely. A starship in interstellar space sits inside that vacuum permanently. It is living inside a thermos it cannot open. Radiation becomes the only exit, and radiation follows a punishing rule. The power a surface radiates scales as its temperature raised to the 4th power. Double the temperature, and you shed 16 times the heat. That sounds helpful until you notice which direction it cuts. A crew habitat must stay near room temperature. You cannot run the living quarters at 400 degrees to make the physics easier. So, a comfortable ship radiates weakly, and to dump serious heat at a comfortable temperature, the radiating surfaces must be enormous. Not panels, wings, fields of them. The cold background helps, and this is the one gift the void offers freely. Deep space sits only a few degrees above absolute zero, so anything warmer than that will always lose heat into it, but only if it can see the dark. A radiator pointed at another part of the ship doesn't shed heat, it trades it. 2 warm surfaces facing each other simply pass energy back and forth. Every radiating surface needs an unobstructed view of empty sky, so the shape of the vessel stops being a structural question and becomes a thermal one. No air means no aerodynamics. Nothing about the design needs to be streamlined. What it needs is for every hot surface to have a clear line of sight into the dark. A starship silhouette is a heat problem wearing a hull. So let's consolidate the honest answer to the question we set out with. What a journey of 1 light year would actually be like. Time comes apart. At the speeds that make the crossing survivable within a human life, the crew's calendar and Earth's calendar separate permanently, and nothing anywhere resynchronizes them. The sky is rewritten, constellations dismantled by aberration, colors reassigned by Doppler shift, most of the visible universe compressed into a blazing circle ahead, and blackness everywhere else. The medium becomes radiation. The thinnest gas in existence turns into a continuous particle beam aimed at the front of the ship. Dust becomes explosives. A grain you could barely see delivers the energy of tons of high explosive into a spot smaller than a pinhead. The body degrades. Bone, muscle, heart and vision, all optimizing for the wrong environment, while heavy ions cut microscopic tracks through tissue without pause for years. Communication decays through 3 stages, from conversation to correspondence to historical archive. The energy required exceeds current planetary output by orders of magnitude, before you account for the mass of everything you added to survive the rest of it. And when you finally stop, you arrive displaced in time as surely as in space. The people who waved you off have lived through years you never experienced. That's the inventory. 1 light year, priced honestly. Now here's what should genuinely astonish you about that list. Every single figure in it was calculated from the ground. No human being has traveled 1,000th of this distance. Not one person has experienced any of it. And yet, we can state, with numbers, with error bars, with confidence, what happens to a clock, a hull, an eye, and a bone across 5.88 trillion miles that no one has ever crossed. That capability took about 4 centuries to build, from Galileo rolling bronze balls down inclined planes in Padua, timing them by pulse and water clock, to the Large Hadron Collider accelerating protons around a 27-kilometer ring, 17 miles of superconducting magnets, measuring particles that exist for fractions of a second. And the extraordinary thing about that method is not that it explains what we've already seen. Any story can do that. The extraordinary thing is that it keeps making predictions before the evidence exists, and the universe keeps agreeing. Einstein's equations predicted that gravity bends starlight. Arthur Eddington measured exactly that during the eclipse of 1919. The same equations predicted that orbiting masses radiate gravitational waves and slowly spiral inward. In 1974, Russell Hulse and Joseph Taylor found a binary pulsar at Arecibo, 2 neutron stars orbiting each other, and tracked its orbit for decades. The measured decay came out at 99.7% of the predicted value, agreement to within a fraction of 1% on a phenomenon nobody could see, from a theory written 60 years earlier. They received the Nobel Prize in 1993, and in September 2015, a century after the prediction, LIGO detected those waves directly. Add the confirmations already sitting in ordinary life, the muons arriving at sea level, the satellite clocks that must be corrected daily, the atomic clocks flown around the world and returning out of step by precisely the predicted nanoseconds. Always the same answer. Not once has the arithmetic been contradicted, which means when the same framework says a crossing of 1 light year costs what it costs, we are not guessing. We are reading a measurement of a place we have never been. That brings a quieter realization, and it deserves to be said plainly. Whoever eventually builds interstellar capability will not be the traveler. The engineers who solve the energy problem will die on Earth. The crew will not be born for generations after them. But we have done exactly this before, and the precedent is instructive. Johannes Kepler published his laws of planetary motion between 1609 and 1619, working from Tycho Brahe's observations by candlelight. Isaac Newton published the Principia in 1687, explaining why those laws held. The first object reached orbit in 1957. Orbital mechanics, the complete working mathematics of spaceflight, was written roughly 350 years before anything flew, by people who could never possibly have used it. They were not building rockets. They were building the knowledge that rockets would one day require. We are standing in the same position now, possibly at a similar distance from the payoff. Let's come back to the distance itself, because it turns out not to be arbitrary, and understanding why reframes the entire problem. Stars form when vast cold clouds of gas and dust fragment and collapse under their own gravity. How those clouds break apart, the tug of war between gravity pulling inward and gas pressure and turbulence pushing back, determines both the typical mass of the resulting stars and how far apart they end up. In our part of the galaxy, that process produced an average separation of roughly 5 light-years between neighbouring stars. But it could easily have been otherwise, and elsewhere it is. Inside a globular cluster, an ancient ball of hundreds of thousands of stars bound together, the average separation drops to something like 1/10 of a light-year. In the dense cores, measurements give figures as small as 3/100ths of a light-year. In the packed centres of some galaxies, stars sit roughly 13,000ths of a light-year apart, around 860 astronomical units, only about 20 times the distance from the Sun to Pluto. Imagine a civilization born there. Their night sky would hold thousands of stars shining as brightly as Venus does to us, and their nearest neighbouring star would be a journey 40 times shorter than ours, perhaps reachable with the kind of engine we have already sketched on paper and abandoned as insufficient. The physics would be identical, the arithmetic would simply come out survivable. So the emptiness around us is not a punishment and not a barrier placed deliberately. The universe is not hostile to us. The universe is indifferent, arranged according to the behaviour of the particular cloud that collapsed to make our sun 4.5 billion years ago in a loose and unhurried way. And that means the distance is information. Those 4 or 5 light years between us and everything else are a measurement of our own origin, a record of how quietly our star was born, which leaves one question genuinely open, and pretending otherwise would be dishonest. Nobody knows whether the energy problem has a civilization-scale solution at all. Not, we haven't built it yet. Something harder. Nobody can currently say whether any physically permitted method exists for moving human-scale mass across these distances at a cost a civilization could actually pay. The gap between what antimatter promises and what any conceivable factory could produce runs to more than 12 orders of magnitude, and no proposal on the table closes it. And a related argument has been running for decades without resolution, whether sending people is ever the rational choice. One side has the numbers. A gram-scale probe needs no food, no air, no gravity, no shielding for a body, no closed ecology, no psychology, and it does not care how long the journey takes. Every problem this story has described becomes vastly smaller or vanishes entirely when the payload is a chip instead of a person. If the goal is knowledge, send the instrument. The other side answers that instruments only return answers to questions we already knew how to ask, that a mind on site adapts, notices and decides, and that a species confined to a single planet carries a risk no probe reduces. Layered over both is a strange strategic problem that Andrew Kennedy named the incentive trap in 2006. If travel speeds keep improving, any ship you launch today will be overtaken by a faster one launched later, so waiting looks rational, forever. Except Kennedy showed the curve has a minimum, an optimum departure time, after which waiting makes you arrive later, not sooner. A 2017 analysis in monthly notices of the Royal Astronomical Society, using 211 years of speed records from steam locomotives to Voyager 1, found historical speed growth much faster than Kennedy had assumed, pulling that optimum dramatically closer to the present. Nobody has settled it, and the answer decides whether any of this is a mission plan or a thought experiment. So let's come back to the original question one final time. and answer it exactly. 1 light year is not a destination. Nothing is there. No one could arrive because arrival requires a somewhere, and the coordinates we have been describing hold nothing at all. 1 light year is a measurement. Look back from that position, and the sun is still the brightest object in the sky, a single point among the others, giving no warmth, casting no shadow, offering nothing but its own presence. In the beginning of this journey it looked like a diminished home, but that spark was never a lesser sun. That spark is a ruler. The light entering that window left our star 1 year ago and travelled without pause the entire time. The distance is the year. Every light year printed in every catalogue is a duration wearing the costume of a length, a statement about how long the universe takes to tell you something, dressed up as how far away it happened. We know what crossing it costs. We know what it does to a clock, to a hull, to a bone, to a conversation. We know what the sky looks like from inside it, down to the colour of the light and the angle of the cone, and we know all of it without having gone. That may be the strangest achievement in this entire story. A species that has never travelled further than its own moon has measured a place 1,000 times beyond its reach. Carefully, honestly, including every number that says we cannot go yet. The distance has not moved, the physics has not softened, but we know it now. And knowing exactly what stands between us and somewhere is how every journey in human history has ever begun. Look up tonight, and you will not see the sky. You will see its past. The moon reaches you 1.5 seconds late. The sun, 8 minutes and 20 seconds. Proxima Centauri, the nearest star to ours, arrives 4 years and 3 months after it left. So the light landing in your eye tonight departed while you were living a life you can still remember. And some of the faint stars you can just barely pick out on a dark night set off hundreds, even thousands of years ago, when no one who loves you had been born. None of it is happening now. None of it ever was. That crew, a light year out, watching their calendar drift away from ours, they never discovered anything new. They only travelled far enough to feel what has always been true of you, sitting exactly where you are. Every face you have ever seen arrived slightly late. Every voice, every star. Distance was never really space. Distance was always time, quietly, in every direction, and you have been receiving the past your entire life without once noticing. That spark in the ship's rear window was never a smaller sun. It was a year, made visible. Thank you for staying with me across all of this. If it moved something in you, a like and a subscribe are how I know. There are quieter journeys still to come. Sleep well. The old light is still arriving,